Hi, welcome to Accelerated Engineering. This is the tutorial on the Lambda function and a related bit of humor or content at the end. If you were looking for a tutorial on a different function, let me know in the comments so that I can get started on that. So the Lambda function is relatively new to Excel, and it is, without a doubt, the most powerful function, hands down. It's also one of the more difficult ones to kind of wrap your head around, which is why there's lots of tutorials and examples of how to use it. The basic idea of a Lambda function is that it allows you to define a calculation or function and then pass it inputs that are arbitrary. What this means is that basically we get to write our own functions into Excel. Now, a simple example of this that we're going to solve today is a solution for the quadratic equation. There is no equation fundamental to Excel that calculates the roots of a quadratic equation. So we're going to write one because that's a fairly useful tool in anybody's toolbox. But first, let's look at how the Lambda function is shaped. It looks like this. We say equals Lambda. I'm going to enter most of my stuff in the formula bar here. It says right away we need a parameter or a calculation. For this one, we'll do a simple example first and say that my parameters are going to be A, B, and C because I already have those values tucked away on the side. For values A, B, and C, I just want my output to be the sum of these values. This is the really easy example. A plus B plus C. And that's it, and I can close that off. Now Excel doesn't know what to do with this yet because I haven't told it what the values of A and B and C are. So now I'm going to set a second set of parentheses up. And this is telling Excel what values to put in. My first value is A, and I'll select this cell right here. Now it shows up as being input A because I've taken the time to name these values in advance. It'll make the next steps easier. So I'm going to have input A, input B, and input C, and close that off. Now when I hit enter, it returns the sum of those three numbers. 1 plus 1 plus minus 5 is equal to minus 3. And if I change that C to be equal to 2, then my answer should be 4. And there you go. Now, the steps that I glazed over, one is under the name manager. I have already set up these values, or these named values for input A is equal to cell F9 over here, and so on through. It's going to make it easier to keep track of what's what when we get into the quadratic solver. What was that? The other thing that I've done to set this up is I've made the calculation ax squared plus bx plus c, a typical quadratic function. I've made it on the other sheet so that it actually calculates the values and spits it out onto a nice graph so that we can keep track of what we're doing. So the quadratic equation, this lovely piece of work here, is designed to return the roots of a quadratic function. The quadratic function must be of the form ax squared plus bx plus c. This is a typical high school level bit of maths. The function then is we want to find any place where this function is equal to 0. And the quick and dirty thing that everybody's memorized in order to solve that is that x, the values at which this function is equal to 0, is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Now, we can see that for these values, 1, 1, and 2, there is no intersection with the 0 line, so we're going to change that and make it equal to minus 5. So now we can see when we solve this, we should be able to find some actual roots to this equation. But it's not one that's easily factored all by itself. So let's write a formula that does this. I'm going to start off with the very familiar equals lambda. And for inputs, I think we want inputs A, B, and C again. And we'll match these up to what's already in the equation. Now, my calculation is going to be another function, the let function, because it will allow me to perform multiple calculations without losing track of anything. And because of the way that I always start my let functions, I always input a test value equal to 1 and then tell it to output the test value. For more information on how the let function works, see my tutorial on that function. And I'll close the lambda, and right away we'll input all of these values. Now, what I'm expecting is, because I haven't told it to manipulate A, B, or C, I'm expecting this to output the value calculated by this let function, which in this case is just going to output 1. I hit enter, shows 1. That's good. It means that I've set this up properly. Okay. Now, I always break up my functions a little bit in order to make sure that I can keep track of everything. So you'll hear me hitting the space bar a whole bunch of times in order to make the spacing work. Okay, well, if I want my output to be the value of x at which this function equals 0, I'm just going to type this equation in. We're going to go, and I'm going to add a parentheses right away, but minus b plus, and I know it says plus or minus, but I'm going to pick plus for now, plus the square root of b squared minus 4 times a times c, close my square root, so I got minus b plus the square root of b squared minus 4 times a times c. All of that needs to be divided by 2a, so I'm going to divide by 2 times a and close. And that's it. If I hit enter, it says that my root for this equation is 1.79 and something, and that looks about right. Now hang on a second, Jonathan, you might say. There's a second root to this equation. There's a negative root, and I can find it easily if I change this plus to a minus. But you know what? And again, that looks about right. Minus 2 3/4 is about there. But this equation only outputs one value. I want to have both. So, well, what can we do about that? The great thing is that Excel will allow us to output things as a dynamic output, or a dynamic array output. So in order to capture both parts of this equation, the fastest and easiest way to do that is to say, I want a V-stack, or a vertical stacked output. And I want to include this original solution, and the next element that I want to have, and I'll just pull a little copy and paste, is the same thing, but with the minus sign. So now we're taking both the upper value root and the lower value root. When I hit enter, now this function outputs 2 values. Again, you can see that it's an array output by the blue line surrounding it. And that works pretty great. Now if I manipulate my values of A, B, and C, my graph automatically updates, and you can see that in this case it tightens up. Now my first one is 0.9 and a bit, my lower one is minus 1.1, and that looks like it's fitting in nicely. So that's good. So I've got my 2 roots, my upper root and my lower root. Say, well, is that all there is to it? What happens for an equation like this, where we can see from the graph that there is no real solution for x equals 0. This line does not cross the x-axis. There is no value. Now, if you're familiar with complex numbers, you'll know that there is a complex solution, where there is a real part to the answer and an imaginary part. And we are going to solve in addition for the imaginary part and have that output. And I'll point out that in the event that there's no solution, this just throws a number error, and That's pretty typical. Okay, so since we're rewriting this, I'm going to write this completely differently. We'll just back that off a notch. Okay. Well, we know whether or not this has real solutions or imaginary solutions, complex solutions, pardon me, based on the determinant of the equation. The determinant is the fancy name for this chunk underneath the square root sign, b squared minus 4ac. The reason it's called the determinant is because if this value is positive, the square root evaluates to something that is a real number, and you have a real solution. If b squared minus 4ac is negative, then the value under the square root is negative, and there's no real square root of a negative number, which means that it returns a complex solution, where we're going to see I, or j, or the root of -1. It's the imaginary number. So what we're going to do for that, since we know that that is the complex part of the number, we're going to write in a value called the determinant. Determinant. And we're going to say that that's equal to b squared minus 4 times a times c. And that's that. That's going to be the part that makes things messy. Now our solution is going to have two parts. We're going to have a real part, which I'm going to call real part. And just in my head, or in our heads, I'm going to take this 2a and distribute it to both sides. I'm going to break this equation up. So the real part of this is going to be minus b divided by 2 times a. That's going to be the real part of my solution. The imaginary part, or the complex part, is going to be equal to the square root of the determinant divided by 2 times a. Okay. That looks good. One more comma needs to go in there. Okay, now how do we want to do this? Well, I know that if my determinant is positive, I'm going to have real numbers, and I can just add the real part and the part that might be complex together, and I'll get my answers. And if the determinant is negative, then I'll take the real part and add or subtract the complex part, and I'll get a complex number. So the way that I want to write that, 5, 6, 7, 8, 9, 10, is that I'm going to say that my output, or my value of output, is if the determinant is less than 0, I'm going to output a complex solution. So I'm going to say it's the complex, which includes the real part, and it includes the complex part. Great, okay. Well, actually, no, hang on. That's only one of my complex roots. If I want to do 2, I'll have to use the v-stack trick again. So I'm going to say v-stack is the complex part, comma, I'll say complex real part, and this time the negative complex part of the equation. Close complex, close v-stack, and that'll give me my roots if the determinant is less than 0. That'll return my complex roots. Okay, great, that's good. I'm going to do the same thing again for the real roots and say v-stack, but this time all I need is the real part plus the complex part and the real part minus the complex part. And that will give me a satisfactory answer for both of the real roots, if there are real roots. Now, did I close all of my functions? I did not. Close the if function, and my last line is going to say that the final variable is output. And this just tells the let function to return the value output, which I've defined. Okay, let's see if that works. A name error. Well, isn't that fun? Okay, after a little bit of troubleshooting, I found the problem. So the problem is that this square root here, taking the square root of the determinant, if the determinant is negative, then Excel has a mini heart attack and can't handle a square root of a negative number natively. So what I need to do here is add the absolute function, which returns the absolute value of the determinant and makes sure that it's always positive. Now that doesn't throw off the mathematics of this because we already have a plus or minus in front of the square root. So it doesn't matter if the contents are positive or negative, and we're handling the complex part more carefully. Now when I hit enter, it still throws me a name function, which I'm going to just hit pause and troubleshoot. And after a little bit more troubleshooting, find out that there is a T missing in output right here. And there we go. That returns two values. And this is what we'd expect from an imaginary pair, is that the real part is the same and the determinant, or pardon me, the complex portion is different. And this will work for all values. Now, this is a little bit hard to look at, so let's add a little bit more to this. And what we're going to do is round off both the real part and the complex part. We're going to say that the real part is going to get rounded, and I think 4 decimal places is enough. So we'll add a 4 there, and then we'll round off the imaginary part. Enter, and there. That's a little bit more digestible. And that's what we would expect from these imaginary roots. And just like that, we have a formula or an equation that solves the quadratic function. Now that's really handy, but it's a lot to type. Now that we've got it working, it'd be nice if I didn't have to type all of this or try and copy and paste this and make sure that it all worked properly. Here's what we can do instead. So we can turn this into our own custom function by grabbing all the portion of this equation that is just the calculation part. So we're leaving out the input values, just the calculation. And let's do a copy and escape out. What I'd like to do is take the name manager and make a new named variable. And we're going to call this formula solve quadratic. Now, don't let it refer to anything. This is the right place to paste in that entire function. Control V, and you get this long, well, everything that we typed in there, just in this nasty little viewer. It's a terrible place to have to try to edit stuff. That's why we do it in this cell. I'm going to hit OK. And that's it. Now I have this solve quadratic variable. Close out of there. Now what we can do is the next time that we've got this problem and we want to do something, I can type solve quadratic. Now it doesn't show up on the video, I think. You can't see, but it actually drops down. It's a selectable formula that Excel recognizes as if it were one of its own native formulas. So I'll solve quadratic and open the parentheses, and it says that this calls for 2 values, A, B, and C. There's my A, my B, and my C, just like that, and done. And it just outputs the roots of that equation. And that is a very handy little bit. This is how Lambda functions work. As long as I save this sheet, I never really have to think about that again. I just have a formula that solves the quadratic equation, which is super handy. Now, if I wanted to move this function to another spreadsheet, all that I would have to do is take this sheet and move or copy it to another spreadsheet. You can open it up in there, and then that formula will transfer over. And in order to make that easy, I'm going to make this spreadsheet available on my Google Drive publicly, which will be linked in the description below. And this concludes the tutorial. And if you're still here, you must now enjoy the humor, because that's the rules. For the lambda function, I wrote a poem. The poem goes like this. Mary had a little lambda, a well-defined function. For any input fed to it, it answered without compunction. And if that answer or that humor doesn't scare you off, consider subscribing for more content like this.